share my screen. Okay, we continue with force vibration of undammed system using modal analysis. I explained how to extract the modal matrix and use the modal analysis method to extract the modal matrix. Today we want to use this method to obtain the response of an undamped system, a multi-degree of freedom undamped system subjected to the external force. We explained that by using the modal analysis method, we can extract the modal matrix, which the modal matrix in fact consists of the mode shapes or modal vectors. And then by using this modal matrix today, we will see that we can convert a system of uncoupled ordinary differential equations from order 2 into a system of n uncoupled differential equations of order 2. So we have the equation of motion as this, in this form, the matrix M, which is the matrix of mass, multiplied by acceleration, matrix K, which is the stiffness, and it's equal to F, which F is the vector of arbitrary external force. From the free vibration, we can obtain the natural frequency and also the mode shape. And as I told you, we can form the modal matrix. We define a new time-dependent generalized coordinates, Q1 to Qn, and they are related to X or the response. For this purpose, we use the modal mode shapes or modal vectors. So as I told you, we form the modal matrix. Modal matrix is consists of the modal vectors or mode shapes. As you can see, the first column is the first mode shape, the second column is the second mode shape, and the nth column is the n mode shape. So we can define xt or the response as a function of the time-dependent generalized coordinates q1 to qn, which we define this as a vector qt. As you can see here, qt is a vector with n components from q1 to qn, and xt, which is the response of the system, and this is again a vector with n components from x1 to xn, and it's equal to the modal matrix multiplied by qt. So if we substitute into the governing equation, instead of x, we substitute modal matrix multiplied by q. So the derivative of x with respect to time is equal to the derivative of q with respect to time, because this modal matrix vector is a constant vector. And if you substitute into the main equation, we will have, instead of x double dot, we will have the matrix x multiplied by q double dot, and instead of x, we will have matrix x multiplied by q. Now we can pre-multiplying the through by matrix transpose, which in fact this is the transpose of the modal matrix. So if you pre-multiply by the main equation, we will have this term x transpose multiplied by m multiplied by x, and x transpose multiplied by k multiplied by x, and the non-homogeneous term, instead of f, we will have the x transpose multiplied by f. So now we can simplify this and we can normalize the vector x as we did it. So we can, instead of this term, we can substitute the result of this equation and simplify. and we know that the X transpose multiplied by M multiplied by X, this term is equal to the matrix I, or the unit matrix. In the unit matrix, the diagonal components are 1 and the other components are 0, and X transpose multiplied by K multiplied by X is again a diagonal matrix, but this time in the diagonal components are omega squared. So we can form this matrix and we can simplify. So instead of the X transpose multiplied by Ft, we define the new generalized force Qt, and then we can substitute into the equation, and you will see that instead of n coupled ODEs, we will have a system of n uncoupled ODEs from order 2 like this, which are Qi double dot plus omega squared Qi is equal to the uppercase QIT, which this is the i's component in this vector, the vector of non-homogeneous term. And we can form n equations of motion for in terms of Q, as you can see, and for each equation we can obtain one response. So we can obtain Q IT for I from 1 to n. So instead of a system with n degree of freedom, we will have n system of single degree of freedom with 1 degree of freedom, and we can solve for each system. We can solve and obtain the response. From the STOF response in previous chapters, you know that we can obtain the response for STOF system subjected to external force by using the convolution integral or any other method that you want to use. You can find the response. So for the ice response for Q or Q sub I, we can use the previous method in the previous chapters, the homogeneous response plus the particular response. The homogeneous response is, as you can see, obtained from the characteristic equation and is a function of the natural frequency. And the particular response can be obtained as a function of the external force or the non-homogeneous term. So in fact, we convert the system with n degree of freedom, we convert it into a system of uncoupled equation of motion, or in other words, we can say that in fact we are converting a system with n degree of freedom into n system with 1 degree of freedom. And now we can solve for each of them separately and obtain the response. And finally, the total response can be obtained. And also for the initial condition, we can use this equation. It can be proved that the initial condition for Q can be extracted from the xt, the initial displacement and initial velocity for Q is equal to X transpose multiplied by M multiplied by initial vector of displacement and velocity for X. So by using this initial condition, you can obtain the constant coefficient in the response, and finally you can extract the total response as a function of time. So this was the procedure to obtain the response for an undamped system. And the next step, we want to obtain the total response of a multi-degree of freedom system with damping. But this time, if we want to consider the damping, the equation of motion will be complicated. And in this course, we only consider a specific case, and we call it the proportional damping. In the proportional damping, it means that the damping coefficient is a function of the stiffness and mass matrix, or in other words, we can write that matrix C is equal to a combination of matrix M and matrix K with two constant coefficients alpha and beta. So if we assume that our system or the damping in our system obeys this rule, so we can substitute into the main equation. You can see that we have a matrix M multiplied by X double dot. We have the matrix C, which instead of C, we substitute this term, alpha times by M plus beta times by K, multiplied by X dot, and plus the matrix K times by X, it's equal to F. Now we can do the same procedure for the modal analysis. I mean, we can obtain the modal matrix by assuming the solution vector as a combination of these natural modes. We can obtain a new form for the equation of motion and simplify this. Instead of X double dot, we will have the matrix X multiplied by Q double dot. Instead of X dot, we will have the matrix X multiplied by Q dot. And instead of X, we will have the matrix X or modal matrix multiplied by Q. Then we can multiplying by X transpose. And then by simplifying this equation, we can extract a new form for the equation of motion. You can see again, we have the unit matrix multiplied by Q double dot. We have alpha multiplied by I plus B multiplied by omega squared, a diagonal vector which its components are omega squared multiplied by Q dot. And for K, we will have again a diagonal matrix which its components are omega squared multiplied by Q, and it's equal to QT. So again, if you expand the matrix form, you can extract n ODE from order 2, as you can see, and which they are independent. You can easily solve these equations, but this time instead of the Q double dot and Q, in addition to these two terms, we have Q dot, or we have damping. And again, you can solve similar to the damped system, damped single degree of freedom system. You can solve this equation and obtain the response for this system. From the previous chapters, you can obtain the response for a system with damping. As you know, we can obtain the response. In this case, the coefficient of the damping, or Q dot, is alpha plus beta omega I squared according to our initial assumption, and omega I is the I's natural frequency of undamped system. So we can substitute and simplify and obtain n response for I from 1 to n. And by using the convolution integral and the previous methods in the previous chapters, you can obtain the response by using the initial condition. As you can see, this is the initial displacement and initial velocity, and this term plus this term is the homogeneous response, and this is the particular response using the convolution integral. So you see that we convert a system with multi-degree of freedom into n system with 1 degree of freedom. Of course, for the system with damping, we used one assumption. We assume that the damping is proportional. It means that the damping is a function of stiffness and the mass of your system. And in fact, this is a special case. But for other cases in this course, we will not discuss because it will be a little complicated and needs more calculation. So in this case only, we study the proportional damping. Any questions so far? Of course, I guess there is some complicated issues in the matrix calculation, but in the example you will see it's very easy, and you can easily find the response by using the modal analysis. Any questions so far? Okay. In this example, we want to find the response for the system with equations of motion as below. As you can see, we have a system with 2 degrees of freedom. We have two equations, so we will have a system with 2 degrees of freedom. There is no damping in the equation of motion, and we have the external force, which is 25 kilonewton for t between 0 and 1, and after t more than 1 or after 1 second, the external force is 0. So we can find the response for this interval, and after this interval, after t is more than 1, the response can be obtained as a homogeneous solution because there is no external force. Only we need the initial condition, which the initial condition can be obtained from the response in this interval. So we have this initial condition, x1 at t is equal to 0 is 1, x1 dot, x2 dot, and x2 at t is equal to 0 are 0. So we can use this initial condition for this interval for the t between 0 and 1 and obtain the total response. But after t more than 1, we cannot use this initial condition, and we should extract a new initial condition for this interval for t more than 1. So we will use the modal analysis method because the external term, the external force, is not a harmonic force. As you can see, this is a constant value. We cannot use the simple method. We cannot consider the response, the particular response, as a harmonic and then substitute into the equation to find it. So we can use the modal analysis method, and for this purpose, we can find and solve the homogeneous solution to obtain the natural frequencies and mode shapes and form the modal matrix. So as I told you, we form the homogeneous response equation, which is k minus m omega squared. This is the matrix of coefficient. It must be equal to 0. And when you find the determinant of this matrix for a non-trivial solution, you can obtain the roots or the natural frequencies. We will have two natural frequencies. The first one is 12.25 and the second one is 38.73 radian per second. So these are the natural frequencies of the system. And now we need to form the mode shapes. To find the mode shapes, we have this equation, k minus m omega squared. You know, this equation comes from the initial assumption. We assume that x, the response, or xi is better, is equal to uppercase xi multiplied by, for example, cosine omega t. Okay, by substituting this solution in the main equation, I mean we substitute here, of course, into the homogeneous form, I mean the f1 when the f1 is 0. If you substitute, we will have this matrix k minus m omega squared. If we form this matrix k minus m omega squared, it will be multiplied by the uppercase x1 and uppercase x2. It must be equal to 0. And from here, we can conclude that the determinant of this matrix, which is k minus m omega squared, must be equal to 0 to find a non-trivial solution, and then we can find the natural frequencies. But this matrix is, in fact, matrix K, which is 150, the first component, minus m omega squared. The m component, the first component, is 200, so it will be minus 200 multiplied by omega squared. The second component is minus 150 minus m omega squared. The second component of m is 0, so here we only have the component of K matrix. The third one is again minus 150, and the last component is 225, the component for matrix K, minus m omega squared, which the component of m is 250, so it will be 250 multiplied by omega squared. If you find the determinant of this matrix, you can solve it for omega and obtain omega 1 and omega 2. But now we have omega 1 and omega 2 and we want to obtain the mode shapes. Here, to find the first mode shape, this term, we can find, substitute omega is equal to omega 1. For example, in the first equation, here, I will substitute, instead of omega, I will substitute 12.25. So here, if you substitute 12.25, you can multiply by x1, and the second term is minus 150 multiplied by x2. So we will have 150 minus 200 multiplied by 12.25, which is the first natural frequency, or omega 1, multiplied by x1 minus 150 multiplied by x2 is equal to 0. And if you simplify this, you can find out from this equation, you can find out that x2 is equal to this term 0.8 multiplied by x1. This is the first mode shape. Of course, if you substitute in the second equation, I mean here, instead of omega, you substitute 12.25 and again extract the equation, we will have minus 150 multiplied by x1 and 225 minus 250 multiplied by 12.25 squared multiplied by x2. Again, you can extract the same relation between x2 and x1. This is the first mode shape. As you can see in the previous section, we obtain these mode shapes. And for the second mode shape, you only need to substitute here, instead of 12.25, you should substitute 38.73 or the omega 2. And once you substitute the omega is equal to omega 2, you can extract that x1 is equal to minus x2. As you can see, this is the second mode shape. So we obtain these mode shapes and the natural frequencies. And the next step, we need to form the modal matrix. As you can see, we have the modal matrix. And to obtain the value of x with superscript 1 and x with superscript 2, we need to normalize the vectors. For this purpose, we know that x1 transpose multiplied by the matrix M multiplied by x1 is equal to 1. So you can find the x with superscript 1 from this equation. It must be equal to 1, and from here we can find that x1 must be equal to 0.053 and x12 is 0.047. And now the modal matrix, which the first vector, the first column is the first vector, this vector. Of course, we substitute, instead of x with superscript 1, we substitute from here 0.053. And the second column of this matrix is the second vector of mode shape, which is 1 and minus 1. Only instead of x with superscript 2, we substitute 0.047. As you can see, the first one is 0 here. The first component is 0.047 and the second one is minus 0.047. So this is the modal matrix, and now we can use this modal matrix to uncouple the equation of motion. For this purpose, we can find q, the initial condition q at t is equal to 0 and q dot at t is equal to 0, which is equal to the, this is the matrix M transpose multiplied by the matrix M, the mass matrix. This is the modal matrix transpose, and this is the vector of initial displacement x1 at t is equal to 0 and x2 at t is equal to 0. So if you substitute x1 at t is equal to 0, I think it was, let's back to the problem description here. X1 at t is equal to 0 is 1 and other initial conditions are 0. So we can substitute into the vector here. This term is 1 and the second term is 0, but you can see that the initial displacement vector for q is not, the second term is not 0 and the first term is not 1, it's 10.6. And for the displacement, again we can substitute, but because the initial velocity for x1 dot and x2 dot is 0, so we can conclude that the initial displacement, initial velocity for q is again 0, okay, because both the components are 0. So x transpose multiplied by m multiplied by 0 is equal to 0. The force is equal to q1 and qt, and this is again obtained from the modal matrix transpose multiplied by ft, and if you simplify and find this, you can find that the qt is equal to this term, and in this case you can see that the both equations will be non-homogeneous. Now we can solve q1 and q2, obtain them by using this data. We have q10, we have the omega 1 from the previous slide. We have q1t, which is this term, and we can substitute here. We have again omega 1, the first natural frequency, and calculate this integral. For the q2, we can obtain from this equation, q20 is obtained here. This is 9.4. We have the second natural frequency. We can substitute. We have the q2t, which is this term, and again omega 2, which is the second natural frequency. So by calculating these two integrals, you can obtain q1 and q2 as a function of time, which are the response. And now we can find the total response x1 and x2. But before that, again, I should mention, as I explained in the initial of this example, I explained that this is the response for the interval t between 0 and 1, because after t more than 1, the equation of motion is a homogeneous equation. So we need this response to find the initial condition, and in fact we should find x1 at t is equal to 1 and x2 at t is equal to 1, and also x1 dot and x2 dot at t is equal to 1. Or for q, again, you should obtain q1 at t is equal to 1 and q2 at t is equal to 1, and also their velocity or their derivatives with respect to time at t is equal to 1. These are the initial condition for the second interval, I mean for t more than 1. And then you can solve again the homogeneous equation by using these initial condition to obtain the response for the second interval. Okay, so this example is finished, and for this example we need more time. We can continue this one tomorrow. If you have any question, please ask, otherwise we can wrap up this session. this procedure. Okay, thank you for your attention. So we continue. We have some examples for the multi-digraph rhythm system, and after that we will discuss the obtaining the natural frequencies and mode shapes, and finally I think next week we can wrap up the this course, and we only have one part which is related to the experimental test and the monitoring of the vibration of the system. Of course, that part is not covered in your exam, and I just want to have an introduction for you for the monitoring of the vibration in the system by using the accelerometers, and it can be useful for you for the later if you want to any career in this field. For the school calendar, what is the problem for the school calendar? What do you mean? About this, I think no, because our final exam will start in week 15, I think. And as far as I know, our final exam for this course for MM366, I decided to conduct in week 16. So it will be in the last days of your week 16. Of course, we should check it with the school, but uh, as far as I know, we don't have the 1 week study break. But again, we can check it with the school, and then I will let you know when everything is finalized. Okay, thank you for your attention, and have a good afternoon, and see you again on tomorrow. Thank you.